Introduction to Quantum Mechanics. Have you ever pondered the fundamental nature of reality? How do particles behave at the smallest scales, where our intuition fails us and the laws of classical physics seem to break down? Welcome to the enigmatic realm of quantum mechanics, a field of study that unravels the mysteries of the subatomic world. To understand quantum mechanics, we must first appreciate the limitations of classical physics. Classical physics, as pioneered by luminaries like Isaac Newton, describes the behavior of objects on a macroscopic scale, from the motion of planets to the trajectory of a baseball. It provides remarkably accurate predictions in our everyday lives, yet it falls short when confronted with the bizarre behavior of particles at the atomic and subatomic levels. The birth of quantum mechanics in the early 20th century revolutionized our understanding of the universe. It emerged from a series of experiments and theoretical breakthroughs that challenged the prevailing Newtonian worldview. One of the pivotal moments came with Max Planck's groundbreaking insight in 1900, when he proposed that energy is quantized, coming in discrete packets he called quanta. This notion laid the foundation for a new era in physics. Central to quantum mechanics is the concept of wave-particle duality. According to this principle, particles like electrons and photons exhibit both particle-like and wave-like properties. They can behave as discrete particles with localized positions, yet they can also spread out like waves, exhibiting interference patterns similar to ripples on a pond. This duality defies our classical intuition but is essential for understanding the behavior of subatomic particles. Another cornerstone of quantum mechanics is the uncertainty principle, formulated by Werner Heisenberg in 1927. It asserts that certain pairs of physical properties, such as position and momentum, cannot be precisely measured simultaneously. The more accurately we know one property, the less precisely we can know the other. This inherent uncertainty challenges our deterministic worldview and underscores the probabilistic nature of quantum mechanics. Perhaps one of the most perplexing concepts in quantum mechanics is superposition. According to this principle, particles can exist in multiple states simultaneously until they are observed. For example, an electron can be in a superposition of spinning both clockwise and counterclockwise until it is measured, at which point it chooses one state. This phenomenon highlights the peculiar nature of quantum reality, where particles defy classical notions of definiteness and determinism. The development of quantum mechanics was not without controversy and debate. Visionaries like Niels Bohr and Erwin Schrödinger grappled with the implications of these new theories, leading to the formulation of the Copenhagen interpretation, which emphasizes the role of observation in collapsing the wave function and determining the outcome of quantum events. Despite its abstract and counterintuitive nature, quantum mechanics lies at the heart of modern physics and technology. It underpins our understanding of atoms, molecules, and the behavior of matter and light. From transistors and lasers to MRI machines and quantum computers, the practical applications of quantum mechanics are vast and far-reaching, shaping the technological landscape of the 21st century. As we embark on this journey into the strange world of subatomic particles, let us embrace the uncertainty and wonder that quantum mechanics offers. It challenges our preconceptions, expands our horizons, and invites us to explore the deepest mysteries of the universe. Now that we've laid the groundwork with an introduction to quantum mechanics, let's delve deeper into the strange world of subatomic particles. These tiny building blocks of matter exhibit behaviors that challenge our classical intuition and stretch the limits of our imagination. At the heart of the subatomic realm lie particles like electrons, protons, and neutrons, which make up the atoms that form the basis of everything in the universe. Yet, as we peer into the microscopic realm, we encounter phenomena that defy our everyday experience. One of the most baffling aspects of subatomic physics is the phenomenon of particle-wave duality. As we mentioned earlier, particles such as electrons and photons can exhibit both particle-like and wave-like properties. This dual nature is vividly illustrated by the double-slit experiment, where particles fired through two slits create an interference pattern on a screen, as if they were waves. This peculiar behavior underscores the wave-particle duality inherent in quantum mechanics. Entanglement is another mind-bending concept in the world of subatomic particles. When particles become entangled, their properties become correlated in such a way that the state of one particle instantly influences the state of another, regardless of the distance between them. This phenomenon, famously referred to as spooky action at a distance by Albert Einstein, challenges our notions of locality and separability, suggesting a deeper interconnectedness at the quantum level. Tunneling is yet another peculiar phenomenon observed in the subatomic realm. According to quantum mechanics, particles can tunnel through energy barriers that would be insurmountable according to classical physics. This phenomenon has profound implications in various fields, from nuclear fusion in stars to the operation of transistors in electronic devices. To explore these phenomena further, scientists have devised ingenious experiments that push the boundaries of our understanding. The Stern-Gerlach experiment, for example, demonstrated the quantized nature of particle spin, revealing that particles possess intrinsic angular momentum that is quantized in discrete units. The EPR paradox, proposed by Einstein, Podolsky, and Rosen in 1935, raised profound questions about the completeness of quantum mechanics. The paradox revolves around the concept of entanglement and the seemingly instantaneous transfer of information between entangled particles, challenging our classical notions of causality and locality. Despite the strangeness of the subatomic world, the insights gleaned from studying these phenomena have led to groundbreaking technologies and applications. Quantum computing, for instance, harnesses the principles of superposition and entanglement to perform computations at speeds unimaginable with classical computers. Similarly, advances in quantum cryptography promise secure communication channels impervious to eavesdropping. As we peer into the depths of the subatomic realm, we are confronted with a reality that defies our classical intuitions yet holds immense promise for the future. From the mysteries of particle-wave duality to the profound implications of entanglement and tunneling, the strange world of subatomic particles continues to captivate and inspire scientists and thinkers alike.